this is one of our polyatomics. This is acetate. Acetate ends in ATE, yes?
The little slide thing with the polyatomics, but some of them have like multiple oxygens, but they're not put together. They're like CHOO instead of CHO2.
I think that usually happens with this. So this is acetate. This is another way to write acetate. This is used in organic chemistry quite a bit. This is acetate. So there's 2 carbons here. There are 3 hydrogens, 2 oxygens. So 2 carbons, 3 hydrogens, 2 oxygens. So these are identical. These are both acetate. Right? Some textbooks use this. Some textbooks use this version here. But I think this is probably one of the ones that you'll see that may be written different. Something like phosphate, phosphite, sulfate, chromate, dichromate. There's no other way that we write them, but for some reason acetate, some textbooks write them differently. But this is probably the one that you want to concern yourself with, to know that this and this both represent acetate. When we combine these two, is that we drop the ATE and we're going to add ic acid. So this becomes, we drop the ATE and it becomes acetic acid. So anything that ends in ATE is going to be ic acid. This is nitrite. Nitrate. So this is nitrite. And because we have nitrite, this becomes, we're going to drop the ITE and we're going to add OUS acid. So this is nitrous acid. So let's do one more here. This plus nitrite, nitrous acid. This is nitrate. Because it ends in ATE, it should end in ic acid. So what would the name of this acid be? Nitric. So this is nitric acid, because this polyatomic ends in ATE. So we can see several examples here. Sulfite, sulfurous acid. Sulfate, sulfuric acid. Phosphate, phosphoric acid. If it's phosphite, it's phosphorus acid. Nitric acid, nitrous acid. But we can use those polyatomic names, ITE, ATE, and know which element or which acid we're going to be using. And I think the last thing we want to cover here is they don't talk about electronegativity and electron or affinity, right? So electronegativity so we talked about electronegativity. Electronegativity is how strong these electrons how strong these atoms of specific elements, how strong is that pull on the electron, right? So this considers the pull on electrons for electronegativity, right? Electronegativity, just how strong does a particular element have on those electrons? And then we have electron affinity, right? This has to do with putting substances, elements, into the gas phase, right? And those electrons will release, right? So energy can be absorbed, energy can be released here, depending if the bond's going to break, if the bond's going to be made here. But how easily those electrons can be moved, right? For electron affinity is, I believe there was another graph from chapter 3 that dealt with the values, those energy values for electron affinity in these elements. But this is on the pool of electrons. This is on the energy that's released or absorbed in the gas phase for specific, for certain elements, okay? But electronegativity and electron affinity do have different meanings there. I think that is it. So I don't want to move into sulfur pentahydrate. Copper 2 sulfate, 5 penta, and then we just put pentahydrate. We can see up here calcium chloride monohydrate because there's only one water attached to that. And now binary covalent molecules. So this is where we use, again, we're reminded of these prefixes here. So when we have compounds such as this, we have carbon, dioxide. Di meaning 2 because we have 2 oxygens. But again, remember we're not putting mono here, right? Mono is reserved for this half, the ending of this binary covalent compound. So an example would be, let's do this one here, is that this is nitrogen monoxide. Mono plus oxide. When you have an O and an O, we're going to drop this O here and we call it monoxide. So we have nitrogen monoxide, not mononitrogen. Mono is reserved for just the ending of the name. Let's go with so if we had something like this, what could we name this using our Greek prefixes? Rhymes with enta. Penta, perfect. That this is penta xenon triphosphide. We want to make sure we always end those in "ide," right? So this would be phosphide. Yes?
If phosphorus is the first one, do we turn it into phosphide as well?
Let's take a look. Let's do 3 of those. And let's do 3 of those. So here, what would we do with phosphorus? Do we leave it or do we add IDE? Take a look at your previous examples here. Leave it, right? So this then becomes phosphorus, triphosphorus, trioxide. Does that help answer? All right, yeah, so we're only putting IDE just for the ending. And if we had to name something like this, this would be, it's what?
Dimanganese trioxide.
Why is it's not dimagnesium? Why is this not dimagnesium?
Because it's metal.
Because it's a metal. What type of bond is this?
Ion.
Ionic bond. What type of bond, Jared, what type of bond is this? It's a covalent bond. So these rules for using the Greek prefixes are strictly just for covalent bonded molecules. is that we have to go back. When we name ionic compounds, we name the cation, then we name the anion. So this is magnesium oxide. Metal to nonmetal. Nonmetal to nonmetal. So there's different. Can we see that, Jared? We're good? All right, yeah. So just I always throw that in there just to make sure that we're applying those different rules to different substances that we have there. And then here, just a bunch of examples. This is incorrect. Yeah, so this one is correct, that one is not correct. OpenStax, come on, you got to do better with your slides here. This is not pentaoxide, right? So this is correct. I'm going to write this one on the board because the slide does have an error on it. N2O5. This is dinitrogen. We use all the prefixes except for mono when it comes to the first one. And then we have to put penta and oxide together. When we have an A and an O, we drop the A, and this becomes pentoxide. So let's take a look at what they did here. They said P4O10. So this is going to be tetraphosphorus. Tetraphosphorus, we have to put deca and oxide together. We're going to drop the A, and this becomes dec oxide, not deca oxide. So it would become dec oxide. Naming our acids. So two types of acids. One is a binary acid. So binary acids look like this. This is a binary acid. Binary acid. So these are our binary acids. Binary, bi meaning two. So all of these acids have two elements to them. So here this is hydrobromic acid. So binary acids begin with hydrogen. So all of them are going to begin with hydrogen. All of these acids release hydrogen protons. When we put these in water, they do end up releasing those hydrogen protons. Yes?
I noticed on the lab you gave us a list of anions that also end in I. Are those the same ones? Excluding oxygen? Bromide, chloride?
Yes, bromide, chloride. So here, when we use, let's go with this one here. So N, in a covalent compound, this is named nitride. But as an acid, we're going to drop the IDE and we're going to add the word ic acid. So instead of bromide, it's bromic acid. Instead of chloride, chloric acid, fluoric acid, iodic acid. They get a little different with here because normally this is sulfide, but this is going to be hydrosulfuric acid, hydrophosphoric acid, not hydrophosphic, because in a covalent compound this is phosphide. But as an acid, we're just going to drop the OUS from phosphorus, and it would be hydrophosphoric acid, hydronitric acid. But yeah, they do have, so we end up dropping the IDE, but for phosphorus, for sulfur, they end up a little bit worded, or named a little bit differently. Okay, does that help? Okay. So all of these are, and let me give the, yeah, because this one's different, one more. So this is hydrophosphoric acid. And it is just one word, hydrophosphoric acid, hydrobromic acid. The acid, there's a space here, but with hydro and the element, there's no space. It is one word. This is hydrophosphoric, hydronitric, hydrobromic, hydrochloric, hydrofluoric, and then we have space acid when we name those. Where we is oxyacids. So oxyacids, we omit that word hydro, and we're going to replace it with ic or OUS acid, and then finally we just name it acid. So oxyacids have oxygen in them. Oxyacids are made with polyatomic ions. So polyatomic ions the list that you have to memorize, all of your polyatomic ions, is in chapter 3. So these are all of your polyatomic ions that you do need to memorize, right? Oh, we don't even see it there. So these are all the polyatomic ions here that is in chapter 3. You don't need to memorize them for this exam, but you do need to memorize them for before exam 2. But all of your polyatomics here are what we need to know for the exam. And the polyatomics are what make acids. So when we see a polyatomic and then a hydrogen out front of it, we can consider that to be an acid. Sulfur, we know what sulfur is. Sulfur doesn't change. Sulfur's in group 6. The charge here is -2. When I add this up plus this, it does have to equal 0. So what's the charge on manganese? It is 2+, and this we use as some Roman numeral here. Sulfur here is still 2-, but this time we have 3 of them. -2 times 3 is -6. So what times 2 is going to give me +6? 3. So here, this is now our Roman numeral. And this is manganese 3 sulfide versus manganese 2 sulfide. This also requires a Roman numeral. There are some specific cases here. So like nickel, silver, and zinc do not require Roman numerals, even though they are in this transition element. Again, that's nickel, silver, zinc, no Roman numeral required. And for this class here, we're just going to concentrate on these 3 here. Indium is also one, or isn't one, but let's just concentrate on tin, Sn, lead, Pb, and thallium, which is Tl, not Ti, Tl. Ti is titanium. So this is thallium, and it is Tl. So these, even though they're not transition elements, tin, lead, and thallium do require a Roman numeral. So if we were to name this, we know the charge of tin. This would be tin 4 oxide. Tin 4 oxide because it's one of those exceptions that we have. Let's try Let's work with these polyatomics just a little bit more. We'll go with some of the examples that we see here. So CO3, we're going to work this backwards here. I'm going to put this here. This is Al, aluminum, 2, and then we have CO3, 3. Well, we're just going to understand. So this means that we have 2 atoms of aluminum. So let's put that over here. This is aluminum, 3 plus, and we also have another aluminum that's also 3 plus. And this means here that we have 3 carbonates. So there's a difference between this. This is carbonate. Well, it's almost carbonate. I haven't put the charge here yet. But this means that there's 3 oxygens. When we put parentheses around this, and let's say I put 4, how many carbonates do I have? 4. How many oxygens do I have? 12. We do have 12, right? How many carbons would I have? 4, right? We just multiply those across. We'll get into that later. But here we have carbonate, another carbonate, and another carbonate. But what's the charge on each carbonate? What is it? 2 minus, yeah. Because if these positive charges add up to 6 plus, these negative charges would have to add up to 6 minus. So this is 2 minus, 2 minus, 2 minus, and we have aluminum carbonate. Let's put carbonate with a transition element. So let's use iron. So iron, let's see. Yeah, I think we're good for this. All right. So we have 3 iron atoms. We have 3 carbonate polyatomic ions. Now this polyatomic ion, what is the charge on this?
-2.
-2. Do we need a Roman numeral for iron?
Yes.
Why?
It's a heavy metal.
It's a transition element, right? Our heavy metals are going to be tin, lead, right? So here, this is a transition element. We need a Roman numeral, but we need the charge on that. -2 times 3 is?
-6.
-6. So what times 3 is going to give us a +6?
2.
2 plus. So here, this is going to be iron what?
2.
Iron 2. Carbonate. So iron 2 carbonate. This is the formula for iron 2 carbonate. What's the empirical formula for this? Yes, this is simply just FeCO3 as our empirical formula, right? So this is our formula here for the compound, and then we have our empirical formula for that as well. Let's do one more here. How about we do this backwards? How about we say, what is the formula for lead? The formula for lead phosphate, No, not phosphorus. Let's use sulfites. Sulfite. So heavy metal, lead's one of the exceptions. It's not a transition element, but we do need its Roman numeral. And this is lead-4 sulfite. All right. So the formula for sulfite is SO3 2 minus. And then we have lead here. So let's recall that this charge here is for sulfate. It's not for each oxygen. The charge on sulfate is 2 minus. So if we had lead-4 sulfate, what's the charge on lead? 4. We know that because that's what the Roman numeral says. So because that Roman numeral says 4, we're going to put 4 plus. Least common multiple between 4 and 2 is 4. They both go into 4. 4 goes into 4 how many times?
Once.
2 goes into 4 how many times?
Twice.
Twice. So this is SO3 2. So here is lead-4 sulfate. And about the parentheses, and just to make sure that we're good on parentheses, let's do potassium hydroxide, and let's do this is simply, if we put these together, we simply get potassium hydroxide. Plus 1, minus 1, we have 1 potassium hydroxide. If we put these together, well, I need 2 of these. So we're going to put calcium. These 2 go in parentheses, and then we get calcium hydroxide. Because there's more than 1 polyatomic. Right? If I had, let's go, magnesium and sulfite, would I need any parentheses for this?
No.
No, because these 2 cancel each other out, so we're just going to write magnesium sulfite, right? Because I don't need more than 1 of these, so we wouldn't use parentheses for that. And hydrates, we'll touch on this subject again here, so we do have some hydrates. Hydrates we're going to be using because we see this copper sulfate here, copper 2 sulfate, has 5 water molecules that are surrounding it. That this calcium chloride substance here has 1 water molecule around that. And we call these hydrates. We do have an experiment this semester where we're going to add some heat to those and remove the water. It's a really good experiment, is that this has a particular color when it's got the water molecules surrounding it. But when we heat it up and it dries and we evaporate that water, it changes color, right? So we use some Bunsen burners, heat those up, and we get a nice, we get a different color for those. But those are what we call hydrates. Using Greek prefixes, mono, di, tri, tetra, penta, hexa, hepta, octa, nona. So please make sure that you do have those. I believe we have them right here. There we go. So these are all your Greek prefixes. If we take a look at copper sulfate, this was copper 2 sulfate that they had. Copper 2 sulfate, and then it was 5. So we can name this copper 2 sulfate. I need a Roman numeral because copper is a transition element. So this becomes copper, Roman numeral 2, space, then we're going to add sulfate here. Copper 2 sulfate, there's 5 waters, so we're going to say that this is a pentahydrate. So copper 2 charge is equal to, we're going to say it's the group number minus the number 8. So oxygen is in group 6, 6 minus 8, -2, that this is calcium oxide. Calcium oxide. magnesium. So here, what's the charge on magnesium? 2 plus, and for sulfur? For those of you, 2 minus, yeah. It's hard to see, it is covered up there. This is in group 6, so this is 2 minus, and then this becomes magnesium sulfide. So our concern here is always these valence electrons. We want to make sure that we match up all of these valence electrons. So in this example here, magnesium, group 2, 2 valence electrons. Sulfur, group 6, 6 valence electrons. We're going to put this one here. Let's put this one down here. We can see that these are all matched up now. There's no unpaired electrons. So as far as paired and unpaired electrons, when we see electrons like this, this is what we call a lone pair of electrons. It is a pair. They're not bonded to anything. This is a lone pair of electrons. And this is what we call an unpaired electron. So I want to pair all of these unpaired electrons up. 2 unpaired electrons. Magnesium is going to donate all of its valence electrons. And again, it is going to donate all of them. They don't donate partial valence electrons. We're gonna obviously get rid of both of those. So here, let's take aluminum, and how about bromine? Aluminum is in group 3. 3 valence electrons. Bromine is in group 7. And notice how I'm putting these in. When we put in valence electrons, there is a system we use. Pretend that there's a box here, and we're just going to, it doesn't matter where you start. You can start from here, 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 but we just kind of go in some clockwise, counterclockwise fashion. We just don't do this, right? Because that makes 0 sense, okay? So we just want to make sure that we have some order to it. So here I started 1, 2, 3, 4, 5, 6, 7, and we ended up over there. Here it goes. I'm going to take this one here, and I'm going to donate it over here. The reason I do this is because students sometimes get afraid to cross the lines. They think they're doing something wrong, but it's perfectly fine. So we still have 2 that aluminum hasn't donated. But in order to make this bond, we have to donate those electrons. So what we're going to do is we're going to bring in another bromine. We're going to donate this one over here. We're going to bring in another bromine. I purposely did this just so that we know. Right? So here I'm going to take this one, and it's going to bond all the way over here. So aluminum has now donated all of its valence electrons. Full valence shell, full valence shell. We can make these bonds, and this simply becomes the cation, 3 plus, the anion, 1 minus, 1 minus, 1 minus. When we're putting these together, let's not forget that all of these charges have to add up to 0. So plus 3, and then we have 3 minus. All the charges cancel out, so this becomes aluminum bromide. So here, group 2, group 5, 2 valence electrons, 5 valence electrons. Yes, Brandon?
What if there's an option for both a covalent and ionic bond? Which do the elements represent?
We're going to see covalent and ionic bonding simultaneously.
Yes.
So that happens with our polyatomics. Okay? We're not going to be at this level. We won't be moving the electrons around. we're just going to understand that polyatomics, such as this, let's take, this is positively charged, this is ammonium, one of your polyatomics, and then let's take a simple one. This is just going to be hydroxide, and this is also polyatomic. This polyatomic ion, this is an ion, right? When we're talking about covalent chemicals like hydrochloric acid, and those are covalent molecules. Even though these are nonmetal to nonmetal, this specific polyatomic ion is still an ion that creates this positive charge. This is creating this negative charge. So because this is set up with covalent properties, and this is also set up with covalent properties, when you take this and bond them together, we get ammonium hydroxide, is that this takes on the properties of both. It contains both ionic properties and it takes the properties of covalent properties. So that's where we're going to see those occur both, is when we're dealing with polyatomics that are bonding to each other. But other than that, this is going to be ionic. We're not going to see any metal to non-metal that have covalent properties. Does that make sense? Okay. So again, we need to transfer all these. This goes over here, this one's going to go over here, but we are left with this single one over here. So we need more valence electrons. So we're going to bring in another magnesium with 2 valence electrons, and this one's going to get bonded here, but we still have this extra one that's unpaired. So we need actually more nitrogen over here. So nitrogen has 5 valence electrons. We're going to take this one, put it here, but we're still left with 2 unpaired. So let's bring in some more magnesium. 2 valence electrons. This one can go here. This one can go here. And everything is now married up. There are no unpaired electrons here. So our formula for this is, because we use 3 magnesiums, we put a subscript. We use 2 nitrogen atoms. We're going to use a subscript 2. And again, we just name the cation, then we name the anion. We get magnesium nitride. And again, we did introduce that method that always works when putting these together. Magnesium is 2 plus, nitrogen is 3 minus. Least common multiple between 2 and 3 is 6. 2 goes into 6 3 times, so I'm going to put a subscript 3. 3 goes into 6 2 times, so I'm going to put a subscript 2. So we get magnesium nitride. What number can 4 and 2 both go into? 4. So here, 4 goes into 4 1 time, so I just need 1 tin atom. 2 goes into 4 2 times, so I need 2 atoms there. Let's see. Then we have, let's do. So this is a transition element, and the name of this is manganese. And then we have sulfur that we're going to turn into sulfide. So remember, all of our anions always end in IDE. Right? So we have chloride, fluoride, sulfide, oxide, hydride, nitride, phosphide, not phosphoride, but phosphide, sulfide. But because this is a transition element, if we take a look at this, oh, that should not be O, let's make this an S. Is that this is also named manganese sulfide. But we can see that the formula is different here, right? So with these, because it's a transition element, we do need transition elements require the use of some Roman numeral to tell us what that charge is. Because remember, there are exceptions to the rule, but something here like ruthenium can be 2, 4, 6, 8, right? We don't know. These are set, +1, +2, aluminum, gallium, go ahead and do it, +3, but these other ones in here just have different oxidation states, different charges. But because of covalent, how do I know this is covalent?
Both non-metals.
These are both nonmetals. And I know that it's polar. I want you to do some word association, and I want you to associate the word polar with the word pull. And as long as the electrons are being pulled, this bond here is a polar bond. This is a polar covalent bond because this electron is being pulled between these two nonmetals. So how are we going to decide how we know which direction that those are being pulled? I touched on this just a little bit. We have what's considered periodic table trends. One was affinity that we talked about. Now we have electronegativity. Right? So electronegativity. Electronegativity is how strong an atom has on electrons. How strong is that pull that any atom has on electrons? So fluorine has the strongest pull on electrons. And any element that's close to fluorine also has a strong pull on electrons. Fluorine has the most. This is 4.0, not 40, but there is a point between these. So this is 4.0, 3.0, 2.5, 3.5. But fluorine has the strongest pull. Now, if we take a look at chlorine, 3.0, and we take a look at hydrogen, hydrogen 2.1, which one has the stronger pull? The chlorine does. So this is how we know which elements have a stronger or weaker pull. Now that pull gets weaker as we go down the periodic table and across over to the left. That pull gets weaker. The electronegativity is weaker. So it is weaker going this way. Right? Our electronegativity increases the closer we get to fluorine. But also notice this. Electronegativity decreases faster going down the periodic table than across the periodic table. Right? We can see these two right here. Oxygen, which is right next to 3.5, but chlorine is only 3.0. Right? 3.0 for nitrogen, but if we go down the periodic table, then we get 2.8. Okay? So it decreases faster going down versus just going across. So this was developed by Linus Pauling. And these values here help us determine what kind of a bond it is that we have. This is considered a polar covalent bond. Balance. You will learn how to draw these in this chapter, but we're just not going to cover it right now. Looking at the periodic table here, well, which one is more electronegative? The oxygen. So between carbon and oxygen, which one has a stronger pull? The one that's closer to fluorine. The oxygen. So the oxygen is the one that has a stronger pull on electron. So each one of these lines represent 2 electrons here. So there's 2 electrons in here. And these electrons here are being pulled by the oxygen. And these electrons down over here are being pulled by the oxygen. And these over here, these are being pulled this direction, and these are being pulled this direction. So which one of these between carbon and oxygen is partially negative? The oxygen. Oxygen is partially negative, and carbon would be partially positive. And I know that even because my arrow's telling me the same thing. Between nitrogen and hydrogen, which one is more electronegative? The nitrogen. So the nitrogen has the stronger pull. So these electrons that are sitting here are being pulled towards the hydrogen. These are being pulled this way. These are being pulled this way. So the nitrogen is partially positive or negative. So this is partially negative, and the hydrogen is partially positive. Now, these numbers here can also be used to tell us the type of bond. So, polar pull, right? These electrons here are being pulled towards the chlorine. Is this a polar bond? Yeah. Is this, oh, yeah, is this a polar bond? Yeah. Is this a polar bond? Yeah. Then we have elements like this. Or molecules like this, not elements, I'm sorry. So here, which one of these is closer to fluorine? Oh, they're both the same. So are these electrons being shared equally, or is one pulling it towards the other? They're equally. So if these are not being pulled, right? We relate the word pull with polarity. If there is no pull here, is this a polar bond? No. This is what we consider a non-polar covalent bond. Non-polar covalent bond. But your book doesn't like to use the word non-polar. The textbook likes to use the word pure covalent. So I'm going to put that here, that this is a pure covalent bond. Non-polar, pure covalent mean the same thing. Okay? So this is a pure covalent bond, this is a polar bond, and then we have with this example here that this is an ionic bond.
And honestly, for any tests, would we still put a non-polar covalent bond, or should we put pure?
Either one.
Okay.
Yeah, either one, non-polar, pure, either one will work. And if I was giving it like a multiple choice thing, I wouldn't put this as A and this as B, right? That's unfair, right? Because they're both correct. All right. So we see the electronegativity difference here, right? Between these non-polar, polar covalent ionic bonds. And we can use this chart here to help us determine these types of bonds. Right? So if we take, let's take sodium chloride, 3.0 and 0.9. So what is the difference between 3.0 and 0.9? 2.1. So the difference here is 2.1. The difference between chloride and hydrogen is what? 0.9. Let's do this one here. How about what's the difference between carbon and hydrogen? 0.4, right? So we have 2.5 minus 2.1, so this is 0.4. So if we take a look here, this should be an equal sign. It should be equal or less than 0.4. But 0.4, as we can see, that the bond between carbon and hydrogen is a nonpolar bond. That the difference between hydrogen and chlorine, 0.9, well, that's definitely between 0.4 and 1.8, but that's going to be a polar covalent bond. And then for ionic bond, anything greater than 1.8, and we can see here that sodium and chloride is going to be the difference between 1.8. So we can also see that as to help us verify that these are in fact either pure covalent polar bonds or ionic bonds that we have here. All right. So let's review this naming. I know we did it in the lab, but I am going to start fresh here just to make sure that everybody's good. So it may seem like review because we did this in the lab. But let's review all of our rules because, again, we do have rules for ionic bonds and covalent bonds. So for ionic bonding, we always name the cation first, right? So the cation is the one with the positive charge, right? I'm going to put this here. And then our anion has that negative charge there. So we always name the cation and then we name the anion. So if we had these two together here, this is my metal, which is a cation. What's the charge on calcium?
2.
And how do we know that it's 2?
The second group.
Because it's in the second group. It's in group 2, so this would be 2+. For oxygen, what is the charge on oxygen? -2, right? For those of you that don't remember, -2. So for our anions, so we should get through the first, we're not going to hit anything from Lewis symbols and structures, but just review ionic covalent bonding, some naming to get an understanding of that. So ionic bonding helps explain how cations are formed, how anions are formed, what happens to the transfer of these electrons. Now, we'll review this again, but there is something we call the octet rule, or maybe we can even shorten that down. The octet rule is generally a rule, like the 8-electron rule, but the octet rule here is that most elements and their atoms want to have 8 electrons in what we call their valence shell. So as we did electron configuration, the electron configuration for sodium 1s2, 2s2, 2p6, 3s1. And then let's take neon. Neon is 1s2, 2s2, 2p6. Let's do one more here. Let's do fluorine. 1s2, 2s2, 2p6. 5. So we'll first take a look at what we consider valence electrons. So if we were to look at neon here, so this is our nucleus for neon, or protons and neutrons. Then we have this first energy level, then we have this other energy level. So this being energy level 1, this being energy level 2. In the first energy level, we're going to put 2 electrons. So here's 2 electrons, one here, and then here in the second energy level, we're going to put 8 electrons. So here, 2, 3, 4, 5, 6, 7, 8 electrons. So this, in the outermost shell here, red, this here is what we call the outermost shell. The outermost shell. This is where we find our valence electrons. Right? So in this outermost shell, we find our valence electrons. And here we can see that neon has 8 valence electrons. There's 1, 2, 3, 4, 5, 6, 7, 8. 8 valence electrons. We also know this because it's in the highest energy level. Energy level 2, energy level 2. That we also have 6 or 8 valence electrons. We can also take a look at the periodic table. Right? Neon is in group 8. It's a noble gas. 8 valence electrons. If we take a look at fluorine, fluorine has 7 valence electrons. It's also in group 7, so we know that it has 7 valence electrons. Sodium is in group 1. Its highest energy level is 3, and we also notice that there's 1 valence electron. So these valence electrons are in what we call the outermost shell. So if we take a look at sodium and fluorine, here is sodium, electron, 1, 2, 4, 5, 6, 7, and 8. So here is our 1 valence electron for sodium. So this is sodium with its 1 valence electron. Then we have fluorine that has 7 valence electrons. Now, this octet rule here, where these elements all want 8 valence electrons in their outermost shell. So here's fluorine, energy level 1, energy level 2, 1, 2, so 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So fluorine has not fulfilled its octet rule. But this electron here, if sodium donates that 1 electron, and ionic bonding is a physical transfer of electrons. A physical transfer of electrons. So sodium says, all right, I'm gonna donate this 1 electron, and that way fluorine will fulfill its outermost shell, and it becomes just like a noble gas now. And in doing so, if this electron here, right, sodium has also fulfilled its 8 valence electrons here, and they're now both very stable. There is exceptions to that rule, and that comes with helium and hydrogen. For helium and hydrogen, it's what we call the duet rule, simply because here, this is hydrogen, helium, this is 1s, 1, this is 1s, 2. How many electrons can we put in that first energy level? Just a maximum of 2. So with helium and hydrogen, we would call it a duet rule because there's simply no more electrons that we can put in there. So this is our ionic bonding that we see here. Covalent bonding. Covalent bonding does not work the same. Ionic bonding happens when we have a metal and some non-metal that make a bond by some physical transfer of electrons. Okay? Metal, non-metal. Covalent bonding. Covalent bonding is sharing some electrons. So with covalent bonding, we can take a look at this here. Now, in this bond here, here's chlorine, group 7, 7 valence electrons. Hydrogen's in group 1, 1 valence electron. For hydrogen, we need to have 2 electrons. For chlorine, we need to have 8 electrons. Okay? Hydrogen's not going to give up its one single electron. But hydrogen will share that electron with chlorine. So this valence of this unpaired valence electron from chlorine will share with hydrogen, so hydrogen now fills its duet rule. And chlorine fills its octet rule because hydrogen is going to share that one single electron with them. And these electrons here are not shared equally. When we take a look at an ionic compound, this is plus, this is negative. This lost an electron because it donated it over here, so this becomes positively charged. This is negatively charged because it gained an electron. And covalent compounds, we don't see that. Because we're sharing them, they're not positive or negative, definitively. But these electrons here, this electron spends way more time around chlorine than it does around hydrogen. Is that chlorine is pulling on that electron that it's sharing. So chlorine is pulling that, and because electrons are negatively charged, if this electron here, and let me point it out, this electron here, if this electron here that's negatively charged is being pulled towards chlorine, it makes chlorine, this is just a delta symbol, it's like an unfinished 8, kind of looks like an S. It represents partially. That chlorine becomes partially negative because it is pulling on that electron. And it's pulling it away from hydrogen. So this way hydrogen becomes partially positive. So in a covalent bond, this is not negative, but it's slightly negative. This isn't positive, but it is slightly positive because of the pull that chlorine has on that. So this here, I put this here on purpose. All I need to know is which direction the electron is being pulled. So I use the arrow here, and on the opposite side of the arrow, I put this mark here to help me remind this is the positive end. Right? This is the positive end, that this is the positive end. So we just need to learn now how we're going to determine which one has a stronger pull on the electron. So this electron, or this here is what we consider to be a polar covalent bond. It's